So in the last lecture we stopped here the last at the number of electrons. Today we learn how to write electronic configuration and remaining theory of the chapter. So what is electronic configuration? Electronic configuration refers to the distribution of electrons in different shells. So how we distribute electrons in different shells, that is called as electronic configuration. There are three rules First rule says that the maximum number of electrons which can be present in any shell of an atom is given by the formula two n square, where n is the number of shell as counted from the nucleus. So first orbit or K shell will have 2 into 1 square, which is equals to 2. Second orbit or L shell will have 2 into 2 square, that is equals to 8. The third orbit or M shell will have 2 into 3 square, which is equals to 18. And the fourth orbit N shell will have 2 into 4 square, which is equals to 32. And this continues in the same manner. The next rule is that the valence shell means the outermost shell, cannot have more than 8 electrons. And last, the third rule, the shells are filled in a stepwise manner. So first the K shell is filled, then the L, then M, then N, and it continues in the same manner. Okay. Now let's come back to electronic configuration. So hydrogen has only one electron, so it will go to the K shell because it's filled in the stepwise manner. Helium has 2 electrons, it again goes to the K shell. Lithium has 3 electrons. The capacity for K shell is of 2 electrons. So 2 electrons goes in the K shell and 1 electron will go in the L shell. Similarly, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8. Now for 11, the capacity for L shell is of 8 electrons. So 2, 8 and 1 electron goes to the M shell. 2, 8, 2, 2, 8, 3, 2, 8, 4, 2, 8, 5, 2, 8, 6, 2, 8, 7, 2, 8, 8, 2, 8. Here there should be 9. The M shell has a capacity of 18 electrons. But according to the second rule, the valence shell cannot have more than 8 electrons. That is why we'll take 8 in the M shell and we'll transfer 1 electron to the N shell. And for calcium, 2, 8, again here there should be 10. Since the valence shell cannot have more than 8 electrons, we'll keep 8 here and we'll transfer 2 electrons to the outermost shell, that is the N shell. Okay, this is electronic configuration. Up next, we'll talk about what noble gases are. Noble gases have stable electronic configuration. That is, their valence shell is complete. So they do not gain, lose or share electrons. Their atoms are extremely unreactive. Okay, so what does valence shell is complete mean? If an atom has 2 electrons in its outermost shell, the outermost shell being the K shell, and K shell has only capacity of 2, so it will be complete. Like if you see over here, this one has its valence shell complete. This is helium, and from second shell onwards, the outermost shell can have a maximum of 8 electrons. So if the outermost shell have 8 electrons other than helium, then we say that it's noble gas, like neon. Another example is argon. So this atoms also are noble gases. So they follow 2 rules. One is the duplet rule. Atoms tend to achieve stable electronic configuration by having two electrons in their outermost shell and that is the K shell, like that of the noble gas helium. Another rule is the octet rule. From the word itself we can make out that a duplet means 2 and octet means 8. So octet rule, atoms tend to achieve stable electronic configuration by having eight electrons in the outermost shell like that of noble gases other than helium. So, noble gases are stable, we saw this. So, duplet rule and octet rule says that other atoms which do not have stable electronic configuration will either try to have the electronic configuration of helium if they are close to helium, or they will try to have the electronic configuration of other noble gases other than helium if they are close to them. So the reason for chemical reactivity. So the reason is to attain a stable electronic configuration of the nearest noble gas. As atoms of elements other than the noble gases are assumed to have unstable electronic configuration. So this is the reason for chemical reactivity. So at least now we can mark what noble gases are. This over here, helium, is a noble gas. Another, we have neon as a noble gas. Then 8 electron in the valence shell. Argon is a noble gas. Okay. Up next, we'll learn what a valency is. In simple terms, if we need to define a valency, we can state that it is the combining capacity of an atom of the elements. So how much will it gain, how much will it lose, or how much will it share electrons? That number of electrons which it can gain, lose or share is called the valency. So how do we determine the valency? Noble gases are stable. So noble gases have valency equal to 0 because they neither gain nor lose electron. Their valency will be 0. Their combining capacity is 0. Next, let's take some examples. Say oxygen. Oxygen, the nearest noble gas to oxygen is neon. So oxygen has an electronic configuration of 2,6. Oxygen, atomic number 8, has an electronic configuration of 2,6. So oxygen, in order to become stable, it needs 2 more electrons. The nearest noble gas is neon. The nearest noble gas is neon, having atomic number 10, electronic configuration 2,8. So oxygen gains 2 electrons in order to have the electronic configuration of neon. So over here it has how many protons? 8. Number of electrons 8. Here it will have protons 8. Remember that an atom does not gain or lose protons, and the number of electrons after gaining 2 electrons becomes 10. So the difference is of 2, and what is more? Electrons are more. So there are 2 more electrons, hence it will get 2 minus as its charge because electrons are negatively charged. Let's take another example. Say aluminium. Aluminium also has the nearest noble gas as neon. See 1, 2 and 3 over here. Over here 1, 2, 3, 4, 5. So nearest noble gas to aluminium is also neon. Aluminium, atomic number 13, electronic configuration 2, 8, 3. Nearest noble gas neon again, 10, 2, 8 is the electronic configuration. So aluminium will lose 3 electrons. So aluminium loses 3 electrons to become Al. Aluminium, number of protons 13, electrons 13, protons do not change, remains 13, electrons 3 lost, so electrons is 10. Now what is more? Protons are more. As protons are more by the number 3 and protons are positively charged particles, that's why aluminium gets the charge as 3 plus. Another example, let's say calcium. Calcium, if we see, it's in the last one and its nearest noble gas is argon. So calcium has the atomic number 20, that is 2, 8, 8, 2. Nearest noble gas is argon 18, electronic configuration 288. So calcium, it loses 2 electrons to form Ca, calcium having protons 20, electrons 20. This one will have protons 20, protons number do not change, and electrons, after losing 2 electrons, it will be 18. So since protons are more, by number 2, calcium gains a charge of plus 2. So if we have to write valency, so valency is the combining capacity. So it loses 2 electrons, it gains 2 electrons, so it has a capacity of combining with 2 atoms, maximum of 2 atoms. That is why its valency is 2. The valency will be 3 over here. And the valency here again is 2. So, while writing valency, we can refer to the outermost electrons and its nearest noble gas. So, this has to gain 1 electron. Gaining 1 electron means negative charge. So, this will become minus 1. Or if it loses 1 electrons, then it will have only 1 proton, because this does not have neutron. It will be left with only 1 proton. That will also create stability in it. That's why its valency is plus minus 1. Helium, being a noble gas, has valency 0. It does not combine with any other atom. This loses 1 electron. By losing 1 electron, it forms plus 1, plus 2, plus 3. For carbon, 1, 2, 3, 4 steps. 1, 2, 3, 4 steps. Carbon, they do not generally lose or gain electron, rather they share electrons. We'll be discussing this, and while we do chemical bonding, we'll just write 4 over here, neither plus nor minus. For nitrogen, 2,5, nearest noble gas neon, it gains 3 electrons. So gaining 3 electrons gives it a negative charge. Minus 2, minus 1, 0, plus 1, plus 2, plus 3, 4, minus 3, minus 2, 6. 2 electrons gaining, that is why minus 2, minus 1, noble gas 0, plus 1, plus 2. So these are the valency of different elements. Okay. To learn the nature, there is a very simple trick. We'll first see how a periodic table is written. We'll learn more in depth about the periodic table in the next chapter, but for now, we'll just see how to write periodic table. So there is something called groups. Groups are vertical columns, and periods are horizontal rows. So we'll be dealing with only 4 periods. There are 7 periods in total, and there are 18 groups in total, of which we'll be dealing mostly with 1, 2, 13, 14, 15, 16, 17, 18. Hydrogen, having valency 1, comes in group 1, plus 1. Helium, noble gas, group 18. 18 is for noble gases. Hydrogen, helium, lithium, plus 1, beryllium, plus 2, this one, boron, plus 3, carbon, 4, valence electron 4 is 14. If valence electron is 5, we place it in the group 15. Helium is the only exception that we place in 18, is because helium is a noble gas. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. If you look closely, according to their valence electrons, we have placed them. If they have one electron in its valence shell, we have placed it in 1, 2, 2, 3, 13, 4, 14, 5, 15. So if you are asked the valence electrons of any element, you can just see the group number and tell the valence electrons it has. So nitrogen will have 5 valence electrons. Neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. This 3 to 12, these are transition elements. We'll learn some transition elements like iron, zinc, etc. But those are not in your syllabus, like you don't need to learn the periodic table for them. Okay, of which there is a very peculiar behavior by some of these elements. Only this 3 pair of elements shows something called as diagonal relationship. In this diagonal relationship, lithium has quite many similar properties to that of magnesium. Beryllium has similar properties that of aluminium, and boron has quite many similar properties that of silicon. So lithium has with magnesium, first pair. Beryllium has with aluminium, second one. And boron has with silicon. Do not get confused, only these 3 pairs of elements show similar properties, the diagonal relationship. The remaining do not show. Of which this third diagonal relationship, boron and silicon are metalloids. The left of this all are metals, the right of this all are non-metals. So, boron number 5 is a metalloid, and silicon number 14 is again a metalloid. The left of this are metals, and the right of this is non-metal. After noble gases, if we see calcium and potassium, they also lie on the left of this. So these are also metals. Hydrogen, though it should be a metal, but it is actually a non-metal. Hydrogen is a very contradictory element. It shows properties many similar to that of metals and many that of non-metals, but it is actually a non-metal. Okay, so we have completed electronic configuration, noble gases, valency, periodic table. Next we'll see what isotopes are. Isotopes are atoms of the same element having same atomic number but different mass number. Okay, we'll learn about three isotopes over here, one that of hydrogen, one that of carbon, and the other that of chlorine. There are other isotopes as well, but we'll be only learning this ones. First example is that of hydrogen. Hydrogen has three isotopes. One is 1H1. The down one represents the atomic number, the upper one represents the mass number. So this one has number of protons 1, number of neutrons 0. Because mass number is 1, mass number is protons plus neutrons. Since this atomic number is 1, it definitely has 1 proton. Since its number of neutrons is 0, that is why the total mass number is 1. This is called protium. The next one is 1H2. This is called deuterium. Protons 1, neutrons 1. And the last 1H3, this is tritium. Protons 1, atomic number is 1 for all of this, so protons is 1 and number of neutrons is 2. See, so these are atoms of the same element. These are all hydrogen having same atomic number, all have the same atomic number, that is 1 over here, but different mass numbers 1, 2 and 3. So this is what an isotope is. So this one is the first example. Second example is of carbon. Carbon again has three isotopes. One is 6, 12, another is C6, 13, and the third is C6, 14. So number of protons, you try it on your own. Protons is 6, neutrons is 6. Protons 6, neutrons 7. Protons 6, neutrons 8. The third and another very important, that hydrogen is an important isotope and chlorine has important isotopes. So chlorine is 1735, one isotope, and the other is 1737. So these are also present in a ratio of 3:1. This ratio is 3:1. Why is this ratio important? We'll come back to this. So here protons is 17, neutrons is 18, protons 17, neutrons 20. Okay. Atomic mass of chlorine. Please take a note, okay? Atomic mass of chlorine is a fraction and not a whole number. Why so? Is because of this ratio that it is present in. Atomic mass is the ratio of the mass of the average of all isotopes of an element to the mass of 1/12 of carbon C612 atom. So we need to take the average of all isotopes of the element and to the mass of 1/12 of carbon C612 atom is because whenever we calculate atomic mass, it is taken with respect to the mass of carbon C612. So the average atomic mass of chlorine atom is equals to 35 is present in 3 and 37 1, total 3 plus 1 4, so we get the average. This will get us 35.5. I am writing this directly, please calculate on your own. 35.5 atomic mass unit. Okay, you may also write this as U only in the modern times. In today's time, we write this only as U, which means unified mass. Okay, so atomic mass of chlorine is a fraction and not a whole number. This may come as a give reason. This is an important give reason. Make sure you learn this very nicely and also prepare all the notes that have been written in your notebook. Another give reason, important. Isotopes have similar chemical properties but different physical properties. Chemical properties are dependent on the electronic configuration of the atom and physical properties are dependent on the atomic mass. Since isotopes are atoms of the same element, please note that this is the main answer to this. I am just defining isotopes because isotopes are atoms of the same element. Having same atomic number so same electronic configuration but different mass numbers. Therefore, isotopes have same chemical properties but different physical properties. And the last topic, what are isobars? With this, we'll conclude the lecture for today. Isobars are atoms of different elements having different atomic numbers. This is a sure thing because different elements have different atomic numbers. But have same mass numbers. Example, look closely in this, you'll find an example. If you look properly, you'll see that over here argon and calcium have same mass number but their atomic numbers are different. So one simple example from the periodic table itself is calcium and argon. There are other examples as well, but remembering this is good enough for your syllabus. From this we conclude today's lecture.